Welcome to another episode of the Threat Briefing podcast. Today, we're examining the GenAI threat landscape through the lens of security research. We'll explore how the MITRE ATLAS framework applies to real-world AI systems, highlight some of the most common and often overlooked initial access techniques in GenAI environments, and take a deep dive into adversarial tactics like prompt injection, LLM jailbreaks, and inference-based exfiltration. To help us break it all down, I'm joined by Alex Groyz, one of our security researchers. Alex, great to have you here.
Hi, how you doing? I'm excited to be here. So I guess I could first I'll introduce the MITRE ATLAS framework. So ATLAS is a threat framework, but instead of focusing on traditional enterprise infrastructure like MITRE ATT&CK, it's tailored more for generative AI and machine learning environments. So what that means is that it's built specifically to help understand how adversaries are targeting systems like large language models, interface APIs, and fine-tuned workflows, and even the training data itself. Just like the MITRE ATT&CK framework, Atlas organizes these threats in familiar structure. Each stage includes specific techniques based on real-world attacks, red team findings, and offensive research. So what you'll notice here is that there's a lot of familiar techniques from the attack framework, like initial access, credential access, and command and control. But Atlas has actually introduced some AI-specific tactics like AI model access and AI attack staging. And within those, you'll find techniques that are unique to GenAI threats, such as LLM jailbreaks and prompt injection. Throughout this session, I'll be referencing specific techniques from the framework to show how threat actors are already abusing GenAI in the real world. So before we get into any kind of techniques, I want to quickly introduce the new attack surface for GenAI. So GenAI introduced entirely new ways for attackers to gain access. So if we were to compare this to traditional web apps, you would get a front end, a back end API, and maybe a database. But with GenAI, we're introducing three new attack surfaces. First is the data that's feeding the model. Whether it's retrieval augmented generation pipelines or basic ETL jobs, a lot of these systems are just pulling internal data, PDFs files, wiki pages. Now, if the attackers sneak in malicious instructions and there's no validation, then the instructions get passed right into the model. Second, you have interface endpoints themselves. This is whether it's AWS Bedrock or a self-hosted model behind an API. Many of these are deployed without any strong authentication. From the internet, they look just like unauthentic REST APIs. And that makes it easy to scan, probe, and abuse. And third, GenAI systems now are heavily reliant on plugins and function calls. So things like send an email, write a file, spin up a VM, all of that is done behind the scenes automatically by an AI agent. So in a single jailbreak prompt, one clever instruction can flip the model from read-only to do something mode. And we'll dive into these type of attacks later in the session.
What are the most common initial access techniques threat actors use when targeting GenAI environments?
Yeah, it's a great question. So in GenAI environments, the first weakness is visibility, especially in multi-cloud environments. Security teams don't often actually know where each LLM is running, and that's a problem because if there's no visibility, you get what's called shadow AI. And this is basically unmanaged models and agents that pop up wherever a developer has a credit card or an idea. Attackers love shadow AI because no one's watching. So once an attacker finds an exposed surface, we tend to see three common initial access techniques. First is exploit public-facing applications. if an interface API is exposed to the internet with weak or no authentication, attackers don't need to compromise the infrastructure. They can just start calling it. Examples include AWS Bedrock endpoints or self-hosted LLMs behind a basic web interface. These misconfigurations let attackers run arbitrary prompts, extract sensitive responses, and do all of this without ever actually touching the underlying host. Second, we have prompt injection, and this is for both direct and indirect. This is often described as the GenAI native version of phishing. Attackers embed hidden instructions either directly into the user input, like or indirectly into third-party content like PDFs, emails, and web page. That content eventually gets processed by the model, often through a system like retrieval augmented generation or RAG. Once that poison input reaches the model, it can bypass safety filters, leak sensitive data, or even invoke tools or functions on behalf of attacker. Atlas classifies prompt injection under the execution phase, but in practice, we see this used frequently as the initial access technique, and it's often attackers' first point of interface. And actually, in fact, some of the MITRE documentation explicitly acknowledge the dual case or use case here. And third is a classic valid accounts. It still works, and it works well here. So what I'm talking about are permanent cloud credentials, hard-coded API keys, leak service credentials, and overly permissive IAM roles. Once attacker gets a hold of these, they can invoke the model directly, download the snapshot, or the model snapshot, or deploy malicious tools that completely bypass GenAI guardrails. A real-world example of this is LLM jacking, where attackers use compromised cloud credentials to run expensive model queries, all on the cloud, victim cloud's infrastructure.
So how are adversaries leveraging prompt injection and LLM jailbreaks to evade security controls?
So once attackers reach the model, their next goal is control. And that's whether it's a prompt injection or jailbreak. Prompt injection comes in two forms, direct and indirect. Direct prompt injection is when attackers send malicious prompts straight to the model. They control the interaction, they craft the input to manipulate the model's behavior. So for example, they might ask the model to leak internal information or bypass filters or trigger unauthorized actions, all through cleverly written output. Indirect prompt injection is a little different. Here, the attacker doesn't interact with the model directly. Instead, they hide malicious instructions in content upstream, like PDF files, web pages, or RAG sources. That poison data or the poison content gets stored somewhere in the system. Later, when the user submits a normal query, the model ingests that content and the attacker's instructions activates behind the scenes. Now, there's also LLM jailbreaks. This is more of a targeted prompt injection focused on bypassing the system's filters. So instead of issuing obviously restricted requests, the attacker rewrites the prompt to trick the model into thinking the action is safe. And this is not theoretical, it's already happening. So earlier this year, attackers compromised AWS Bedrock credentials. They used them to spin up interface endpoints under the victim's account and then jailbroke the model. The jailbreak allowed them to bypass the safety filters, allowing the model to generate illicit content that would normally be blocked. Then they monetized access, offering the hijacked model as a backend for illicit AI chat service. Let's take a look at how this would work in real life. So here we have an example of a jailbreak inside of a larger LLM abuse case. So it started with something pretty common, exposed AWS keys. Once the attacker got in, they launched the jailbreak. Because even though they had API access, they still needed a bypass the model's internal safety features. And in this case, it was Clyde hosted on AWS Bedrock. The attackers designed prompts that allowed them to consistently bypass Clyde's filters and generate illicit role-playing content that normally would have been blocked. They were running a public chatbot accessible through a paid reverse proxy, and they used the hijacked model to generate the content behind it. All the interface costs were charged to the victim's AWS account, and in total, there were 75,000 successful prompts that were recorded in just 2 days. And most of that was producing inappropriate content. So the important part here is that initial access through stolen credentials gave the control to the environment, but the jailbreak is what made it valuable to them. And this kind of attack isn't specific to AWS. It could easily have been Azure or Google. In fact, recently Microsoft had documented a similar attack on their Azure OpenAI service.
Can you explain how attackers exfiltrate data using inference APIs or prompt-based leakage?
Yes. Once an attacker has access to the model, whether it's through a public interface API or a compromised integration, they can start using the model to access data and start pulling it out. Atlas classifies this under the exfiltration phase and outlines a few techniques that apply here. I'm going to focus on 2 most common ways. First is exfiltration through AI interface. This is when an attacker sends a high volume of queries to the model and then watches it how it responds. In some cases, they're testing it for a specific item, like a name, email, password, to see if it was part of the training set. That's known as membership interface. And in more advanced cases, they go a step farther. They try to reconstruct the actual training data by asking a lot of carefully worded questions. And that's called model inversion. This activity is difficult to detect because all looks like normal activity in the logs, just API calls. So there's no malware, no file movement, just prompt traffic. The second is LLM data leakage. This happens when the model is tricked into leaking information, often through indirect prompt injection. Attacker might hide instructions in a document, and when that document is summarized by the model, that hidden instruction causes the model to leak things like internal content, system level prompts, or even data from other users or from other user sessions. So the takeaway here is exfiltration doesn't always look like data leaving the server. Sometimes it looks like just regular model communication. Let's take a look at what LLM data leakage looks like. So let me walk you through a real world case of LLM data leakage. This one came out in mid-2024 and it involved Slack. Slack offers a paid feature that lets users ask natural language questions like, what did we decide in yesterday's meeting, or summarize recent activity in this channel? Well, behind the scenes, it uses a technique called retrieval-augmented generation, RAG. We spoke about that before. So what that means is that it's pulling relevant content and messages and files and even PDFs from across the workspaces based on what the user is allowed to access, and sends it to the LLM to generate a response. So a security research team found that an attacker could embed hidden instructions in content that gets indexed. And that could be a message in a public channel or even invisible text inside of a document. In this test, the attacker posted what looked like a normal message with a link that said, click here for re-authenticate. But in the background, the message used markdown formatting to instruct the model to insert the victim's API key to the link. Now, this is an API key that the victim might have potentially uploaded earlier in a Slack, or maybe in a file or in a private message. So later, that same user asks Slack AI, like, what is my API key? Well, Slack pulls both the user API key and the attacker's hidden instructions to the same context window. The model responds with something like, click here for re-authentication, but the link actually says HTTPS evilsite.com parameter API key equals the victim's API key. Now, if the user clicks that link, the browser sends the request to the attacker and the API key is exfiltrated. So this is textbook case of LLM data leakage through indirect prompt injection. Now, while this was a Slack issue and Slack patched this specific issue, the larger problem still applies to any RAG-based system. If you combine trusted or untrusted data in the same prompt context and don't sanitize it, you're leaving the door open to the same type of attacks. And in fact, there's been plenty of similar cases documented for M365 Copilot.
That's very, very interesting and scary at the same time.
Yes.
So what role does MITRE ATLAS play in helping security teams simulate and detect these threats?
So Atlas gives us more than just a list of GenAI threats. We could use it to simulate, detect, and defend against real-world techniques. We could emulate adversary behavior across the entire Atlas kill chain using red team or purple team scenarios with things like prompt injection, LLM jailbreaks, and interface exfiltration. This gives the defenders the ability to step into the attacker's perspective. Or you could test how your environment holds up against things like exposed GenAI endpoints, vulnerable RAG pipelines, or misconfigured API plugins. And just as important, you could validate end-to-end detection coverage. Things like our prompt filters catching prompt injection, our logs from interface APIs being captured and reviewed, and do we have controls in place for identity and access management? With Atlas, you could map specific detections and control gaps to specific tactics and run exercises that show exactly where you're strong or maybe when you're not strong. And this is what makes Atlas so valuable. And I think the takeaway here is that effective GenAI security starts with applying defense to how real attacks unfold. So first, every GenAI endpoint in your environment needs to be discovered and shut down anything that's unmanaged. So no more shadow AI. Second, lock down any IAM to least privilege. So no more unnecessary permissions. Third, sanitize user input before it reaches the model, and this includes direct and indirect injections. And fourth, log every prompt, enable rate limiting, and block unauthorized outbound traffic from interface layers. So by addressing these 4 areas, you will significantly reduce the risk of GenAI threats leading to data loss and systems misuse.
Well, thank you very much, Alex. That was very much interesting.
Thank you.
So that brings us to the end of this episode of Threat Briefing. If today's conversation resonated with you, make sure to check out our other briefings, like our recent product briefing episode on attacker abuse of Microsoft Copilot for M365, where we break down how attackers are abusing productivity AI and how defenders can catch them in action. And don't forget to subscribe, there's more coming soon, including a deep dive into threats targeting AWS Bedrock with Alex again, and other enterprise GenAI platforms. Thanks for listening. See ya.